All right, so let's take a look at some more of these hands-on projects here. That one we've already done, but decision trees we talked about. These things are pretty awesome, and they're easy to understand. So if you go down here, we're going to use the iris data set. This is a famous machine learning task where you have 50 flowers that were measured, three properties of the flower, petal width, petal length, and some other length, 50 in each of three categories of species. So here you can input the data, and this is a decision tree. So the first decision is petal length less than 2.45. If it's true, you go this way. If it's false, you go that way. And then you take petal width, is that less than or equal to 1.75? If it's true, you go this way. If it's false, you go that way. And you're trying to separate the three categories. And so you measure it by this thing called the Gini uh, impurity, which is basically the same thing as entropy. So up here you have 50 and 50 and 50, all three categories equally represented. So that's highly impure, and you get a Gini of 0.667. But here, you perfectly isolated one group. All 50 samples of this group are here and there's no contamination, so that's an impurity of 0. So this is perfectly sorted. This decision imperfectly sorts it. You have 49 correct and 5 incorrect. Here you have 45 correct and 1 incorrect. So these are pretty pure, but not perfectly pure. So the Gini has fallen down to 0.16 or 0.04. So that's how it looks, and you can plot the difference. And you see this, the first if statement does this, the second if statement does that. So you can run this and you can do a graph of it. If you change it to depth of 3, this one will not have any more work done on it because it's done. But the next level will split these up and again lower the impurity. And this one here gets down to totally pure, but you haven't really caught all the representatives of that group. Some of them are still scattered into other categories. So that's a game. And now you can set up a data set like this. This is one we've used before, x times cosine x plus noise. So we're just having a more complicated curve. And you can fit it with a decision tree. So here's a decision tree with a depth of 2. So it sorts things into these 4 categories. And therefore, it can only approximate the curve with 4 horizontal lines. So it's pretty bad. But if you go down to depth 6, it gets pretty good. Now you have, in principle, I guess, 32 to the 6, 64 possible locations, something like that. And unlimited depth, it'll spike every point. So we've seen this one before, but you can do it hands-on and see how it goes. Decision trees are easy to understand and easy to adjust, but they're not terribly powerful. However, what is powerful, in fact, one of the most powerful large learning models, or most powerful machine learning models, is a random forest, which is just a group of hundreds of decision trees. And often you have decision trees where you put the thresholds at random locations even. So you can make, here we're going to make some data to sort, which is blue dots and green dots that overlap some but have some tendency to be separated. So you could draw some kind of decision boundary between them and sort them to some extent. And we're going to make ensemble learning here, where you make multiple different kinds of machine learning models and then combine them together, hoping that the errors will cancel out. So we're going to do logistic regression, support vector machines, and random forest. And so the it trains these classifiers. So here's the classifiers alone. They have this accuracy, 86%, 89%, and 89%. But when you combine all three of them, they go up to 91%. And this is a voting classifier where they're just trying to decide if this area is blue or green. And so you take the votes. If 2 out of 3 of them say it's blue, it's blue. If 2 out of 3 of them say it's green, it's green. So that's treating the output of each model as a hard binary choice, blue or green. And that, as we talked about before, is actually kind of foolish because these models do not produce binary digitized output. They produce an analog signal. So you might as well keep the whole analog signal, and then you have more information. And if you do that, then the soft voting classifier goes up to 92% accurate because it keeps more of the actual information put up on them. And next thing is bagging is another technique that is common. You make random subsamples of the training set to train your model on. So the different models will get different random samples, and that will hopefully cause them to have different uncorrelated errors. So here we make 500 trees using subsets, and you end up with this kind of thing. A single decision tree will overfit the data like this. It's fit this crazy pattern where the oranges are here, but there's more oranges there and there's greens in between. It's clearly fitting noise more than signal. But when you do the 500 trees with bagging, you do smoothly draw a curve through the decision boundary without wasting your time getting caught on the noise points because some of your trees were trained without those points, so they aren't distorted by it. And so you can change your number of trees and such to see how well it goes. And there's a thing called adaptive boosting, where you have a predictor and then you take the errors of this predictor and have a correction term on it, which is a separate machine learning model, and a correction on that one. That's another way to do it. And then you're going to have a learning rate as it goes. Now, if the learning rate is too high, if it makes big changes, then what will happen is it starts here with this 1, then it jumps to 2, then 3, then 4, then 5, because you're making big jumps in the parameters that jump right over the minimum to some bad place on the other side and bad place on this side, and you don't converge. But if you slow down the learning to half the speed, then you get what you want, where it just gradually settles to a nice, reasonable boundary between the two elements. All right. And so here you've got some flags to find, playing with that. So those are good techniques to practice. And now we can do a little bit of mathematics. This is an incredibly important issue. Consider a Tesla. You're trying to drive a car down the road and you have a camera, and there's a video camera in the front, and I think there's more cameras going other directions too, but the camera up front is probably high resolution, like 4K by 4K, and it's probably taking a lot of samples, like 30 samples per second. So that's a lot of data. You've got like 16 megabytes of data coming in, probably times 3 for 3 colors, times 30 or 60 times a second. That's an incredible amount of data coming in. And this you cannot tolerate. And by the way, your human brain cannot tolerate it either. If you had to tolerate all the data coming in your visual system, you'd never get anything done. And yet, if I throw a baseball at your head will jerk out of the way as an involuntary reflex. Within 50 milliseconds, your brain is able to figure out that something is coming fast, it's going to hit me in the head, and your head jerks out of the way. So it's able to determine what the important information is and focus on that and ignore all the unimportant information really efficiently. And that's what every AI must do. And you can see it in a simple way. Consider this. If I have a range, like from 0 to 1 in X and 0 to 1 in Y, and I want to model the behavior of the data, how many points do I need? Well, here I have like 6 points in the middle. Seems like you'd need maybe 5 or 10 points tracing it out, and they have to be kind of evenly distributed. If all your points are on the edge, if all you have is a point near this edge and a point near that edge, you wouldn't have any information about how it behaves in the middle. So an interesting question is, if I have randomly sampled points, how close are they to an edge? And in 2 dimensions, so if I consider, I'm just going to randomly make points in various numbers of dimensions. I'm going to find out how many points are within 1% of an edge. And of course, it turns out if I'm in 2 dimensions, only 25 out of 1,000 points are on the edge. But if I go up to a high number of dimensions, like 1,000 dimensions, all the points are on an edge. Because if I have 1,000 dimensions, I've chosen 1,000 random locations for a point, and one of those coordinates is going to be below 0.01 along one of those dimensions. So every point, no matter how many samples I take, every point is on an edge. The points are not in the middle, tracing out the shape like they need to be, which is another way of saying the same thing I said before. If you wanted to actually make an internal representation of all the information coming in your eyes, you would never succeed, no matter how powerful your brain is. You couldn't possibly do that. But the point is, you don't have to do that. You don't really need to understand 100% of what's out there in the world. All you need to do is find the important stuff, like food, like danger, things like that. And this is, we can get into like religion and the Buddhist stuff where they say the world is an illusion. The world really is an illusion. If you tried to grasp the entire real world, you couldn't possibly process it. You have thrown away almost all the information in the real world in order to focus on the part that you need to know about and ignore all the rest. So you can calculate it here with, you see that this one way to look at it is that no matter how many samples you take, you don't have enough data at all to trace out the behavior of the curve. Another way to look at it is the distance between points. Here, if this goes from 0 to 1, my points are only like 0.2 apart or something, so I trace things out. But the same thing will happen. What's the average distance between 2 points in a high number of dimensions? And the answer is like 400. And this is in a hypercube of size 1. The cube only goes 0 to 1 in many dimensions, but 2 points are 400 apart. So the idea that you can trace out the actual behavior of the phenomenon underlying those points is hopelessly out of reach. So what you have to do is principal component analysis. And what you do here is you have a high dimensional space with a cloud of dots in it, but you say, well, do I really need all that information? Remember we did with the housing. We'd have all these measures about the people living in a zone in California. We'd say, which one of those numbers actually tells me what the price of the house is? And it turns out that even though there will be 10 things being measured, only a couple of them are actually very helpful to predict the name of the price of the house. And that's what's happening here. So what you do is you want to take what are the principal components. I don't want to take all the information in the image. I want to find the features in the image that most efficiently predict what I want to know and are therefore important. And if you visualize it in a hyperdimensional space, what you're doing is taking the cloud of dots and putting a plane through the dots that captures most of their behavior so that most of the variation is in the plane and they don't deviate far off the plane, which means you project them into a lower dimensional space, preserving the important part of their diversity and collapsing the part that was perpendicular to that plane, which it turns out is not important to you anyway. So we take some of these images, we're trying to sort them into 10 categories to see what digits they are. And then you want to choose the right number of dimensions. So you can use principal component analysis and say, I want to get 95% of the variance captured. The original images have 784 pixels, so that's 784 dimensions of information, but I can catch 95% of the variance with only 154 dimensions. So that's a significant decline, and you can do more. You can classify them with a random forest, and the best fit here, where you let it do principal component analysis and settle it down, it found out you can use only 23 dimensions, and you can get an accuracy of 85%. Sorting those images. So now you might wonder, you had 784 dimensions and you shrunk it down to 23. How much damage have I done to those images? You can reconstruct the image keeping only the principal components. So here's the original and here's the compressed. And as you can see, the images are pretty distorted, but you can still see it's a 4. I guess you can see it's a 2 and a 9 and so on. This is what you have. And this is what's really going on in essentially all machine learning data that takes real data from the real world, all like the human brain. All of our sensors bring in far too much data. So at a very early stage, you have to filter it out. And there's a famous psychology experiment where they have a video of students playing basketball, and they tell you to watch the basketball and see how many times it gets passed from person to person. And if you're doing that, a person wearing a gorilla suit has a unicycle and they ride it right through the game and you don't see them, because you're focusing on the basketball. And that's the point. You have this feature to pay attention to something, which is super important. And when you are paying attention to something, everything else is completely removed at a low level of your visual system. So even something ridiculous and unusual will be ignored because it isn't the thing you're paying attention to. And you have to do that. So like I say, the idea that machines are intelligent, you have to take it with a grain of salt. The humans have to put in all these judgments. I see, Zin, you got your hand up? Or Sable, perhaps. Need something? That's the most amazing demonstration when you do that live.
Yeah, I was we did the video with a room of instructors during instructor training.
Yeah.
And I had heard about the video, but I hadn't actually tried it. So
Oh, yeah.
even I knew there was going to be a gorilla, I missed the gorilla.
Yep. I did
And
it
at the end,
first.
when they said,
Yeah.
Sam, your job is to count all the blue shirts. Sable, your job is to count all the white shirts.
Yeah.
And then at the end, they say, like, what color shirt was the gorilla wearing? And you go, what gorilla? It's
That's right.
amazing.
Yeah. There's similar courtroom demonstrations too, where they have somebody come in and like shoot a fake gun at somebody, and then they ask, was that a man or a woman? What color was their hair? What color was their clothes? And they get all random answers from everybody. And it happened in my classroom too. We had a big presentation for Microsoft. There were like 300 students in the room. And one of the students put his laptop on the front table and plugged it in to charge it. And when he went to get it, it was gone. Somebody walked right into a room full of 100 people, 300 people stole somebody's laptop and walked out. Nobody saw a thing. Because, if you don't act suspicious, it just gets filtered out. Oh, somebody picked up their laptop. It's, yeah, I mean, that's why it's important. And so anyway, that's real important how you, the principal component analysis. And the last one, I guess I'll mention, we've always talked about before too, is k-means clustering, where you can see how this works. You can make clusters of dots, and it'll sort them into here, and you can run it. So it starts with random locations, and you can watch how it goes. Here's the first label, and then you put the center somewhere. You take all the dots and label them with the centroid they're closest to, and then calculate the new average of all these points and move it there. And so when you get reasonably close, it works, and you have a measure of error that's going down and down. But if you have a really bad start like this, where it tries to put 3 dots over here and 2 over there, then it will converge to a local minimum, not the global minimum. As you can see, now it will combine these 2 together into 1, and it'll split this big one into 2. So you get a bad fit. This is something that can happen with it. And another thing, of course, is if you change the scale, change the Y scale to go by tens instead of ones, just like before, now you have told it that vertical errors are much, much more important than horizontal errors. So it's going to converge into categories like this, which are very far from what you wanted. But that is what happens when you don't normalize the data. It regards this error as less important than that error. So then you can make a moon-shaped data set. And when I got this from a textbook, they said the moon-shaped data set, it doesn't work very well. I thought it worked pretty well. You give it 8 and it breaks them into groups. And now you have another layer that combines these 3 back into one group. They say, well, it didn't sort them into 2 categories. I say, well, okay, but I could easily take this model and then add another layer that does something very simple, and I would get my job done, where these are separated in a different category than that. So I think it's useful, but it certainly isn't enough all by itself. But here's where you get to do something very interesting. Now, we talked before about how if you have a bunch of unlabeled data, how do you make it labeled? Well, you could mask part of it. That's one way. But if you actually want it labeled, you'd have to pay a human to label it. So let's look at how you can do that. Here, we have another one of these data sets full of handwritten digits, and the answers. And so here's the first 51 shown by the labels, which came with the data. And the real data has 1,797 images. But suppose we didn't have labels. Now, if you just fed a model to the whole labeled training set, which you can do, then you'll get 90.68% accuracy. Okay. Now, but what if you only didn't have labeled data and you don't want to pay for it all to be labeled? Suppose I just take the first 50 instances and train on that. Well, then you get much worse. Instead of 90%, you get 74%, which makes sense. So what you can do is you can use k-means to form 50 clusters, and then you can pick images that are near the center of each cluster. So now instead of just paying to label the first 50 images, I first use k-means to find representative images, and I pay someone to label those images. So label them by hand, label them, and now train on the representative images, and now your accuracy goes over 80%. So that shows, of course, that learning on representative images is much better than just learning on random images. Now that makes some sense, but you can do a lot more. Now what you can do is you can propagate the labels to the instances. You have 50 clusters, and you have a label, so apply that label to all the images of the cluster. I only pay for 50 labels, but I use k-means to propagate the labels, and now the accuracy goes up 85%. And now you can do something worse. Remember up here, there were some dots that were mislabeled because if I go to the good one here, these dots really belong in this group, but it mislabeled them in this group, and that's because k-means works by just taking the closest distance to the centroid, and that would only make sense if all the clusters have the same standard deviation. If they have different standard deviation like this, then you get some things on the edge that are actually assigned to the wrong label. So since you know that can happen, then instead of just propagating the labels to all the clusters, you remove the outliers. Now you take the 1% of images that are furthest from the cluster and throw them away because they probably got labeled wrong. And then your accuracy is still around 85, but in some trials it gets better. There's some random variation. But that's the kind of thinking you can do to benefit from these things. Like I say, these clustering algorithms can be more useful than you think they are. All right. And those are the ones I wanted to show you right now. Let me stop this recording.